Hello there, and welcome back. In this video, we're going to continue our discussion of elementary statistics. In the previous videos, we discussed some of the basic fundamentals that are crucial to the understanding of statistics, including samples, populations, and several measures of central tendency, position, and variation. In this video, we're going to focus primarily on one special way of representing data, and that is in the form of frequency distributions. Frequency distributions typically come in two types. Two types. The very first type of frequency distribution that we're going to be spending a lot of time on is repetitive based. So repetitive based frequency distributions. And the second type is going to be class based. So class based frequency distributions. Repetitive based is probably the most fundamental of them all. There's several pros and cons associated to class based, so I'm only going to be briefly talking about that just for a couple minutes. So let's talk about what it means to be a repetitive based frequency distribution representation for a data set. So let's just start off with an example. So a data set S. So let's S be the set containing the elements 4, 4, 5, 5, 5, 5, 5, 5, and then 7, 7, 7, and then 10, 10, 10, and 10. Notice that there are several repetitive elements in this particular data set, and I'm going to be calling the amount of times that each of these elements repeat the frequency of that element. So for example, I have two 4s, therefore I'm going to say that the frequency of 4 is equal to 2. I have 6 elements of 5, so I'm going to say the frequency of 5 is equal to 6. I have 3 elements of 7, so I'm going to say that the frequency of 7 is equal to 3. And I have 4 10s, therefore I'm going to say that the frequency of 10 is equal to 4. And of course, it's important to know how many unique elements that we have, and we're going to call that C. So we're going to let C denote the number of unique elements, not just elements, but the number of unique elements of S. So in this case, we have that the number of unique elements is equal to 4, in particular the numbers 4, 5, 7, and 10. And why do we use the letter C? Like, why don't we use the letter U or E or something like that? So C is going to correspond to the categories. And when we get to class-based, it's going to be pretty much synonymous to the classes. So it's the set of all values that pretty much uniquely describe the data set or partition the data set. I guess you could also think of it as. So there's several representations of frequency distributions. So first off, you could list elements in the set notation, but sometimes this is extremely difficult to read and interpret, and it's easy to forget an element, especially if it repeats several times. So you could represent this in a table fashion, which we're going to be focusing on. So our unique elements are going to be 4, 5, 7, and 10, and the corresponding frequencies are going to be 2, 6, 3, and 4 respectively. Okay, so this is my table for my frequency distribution for my data set. Since we have a table of values, we can of course construct a scatter plot representation. So x and f of x on the vertical axis. So this is going to be the scatter plot representation. So we have the elements 4, 5, 7, and 10. And of course, for the horizontal axis here is not labeled to scale, so it might be slightly misleading. And then we would put the frequencies, so 1, 2, 3, 4, 5, and 6 on the vertical axis. We have 2 for 4, 6 for 5, 3 for 7, and 4 for 10. Some people will connect these dots for the frequency distribution and construct what people refer to as the frequency polygon for the data set, but it sometimes isn't used in data sets, but at least you should be aware of it just in case you do encounter it. That's called the frequency polygon. Now, of course, if you have several dots, it might be hard to view the scatterplot representation. So what you can do is you can do a bar graph representation of the same exact data set. So a bar graph. So again, we're going to put 4, 5, 7, and 10 are classes or categories on the horizontal axis. And then we're going to just draw bars whose height corresponds to the corresponding frequencies. So that's going to be 2, 6, I'm just sketching the heights here, of course, and then 4. right? So that's the bar graph representation. It's usually easy to see the heights compared to, say, a bunch of dots. It's just usually, and also can add some colors here, like you can make all of them blue. You can put a background. You can do lots of things to make it pretty if you want, compared to a scatter plot, which is a bunch of dots with, pros and cons. Now, one important thing you need to note about, for example, the bar graph representation, and these need not be numerical data values. They could be categorical. For example, they could be the colors red, orange, green, and blue, and how many people responded with those being our favorite colors. That's perfectly fine. Technically, you could do the same for a scatterplot representation, but bar graphs tend to be the most traditional approach for categorical representations. But you can use bar graphs for both categorical and numerical data sets. So either is perfectly fine, whichever one suits your style of presentations of data. So from these frequency distributions, can we calculate, for example, our measures of position, measures of central tendency, measures of variation from the frequency distribution? Because it's possible that we don't have the entire data set, we only have the frequency distribution or an estimate of the frequency distribution to work with. So it's impossible that you should be able to calculate any of your metrics that you want from whatever representation of data that you're sort of working with. So let's just calculate. So let's work on calculating x bar from our frequency distribution f of x. So of course this is a measure of central tendency, and it's one of the more common measures of central tendency that people use, so that's why I'm sort of focusing on that. So the frequency distribution of a data set, remember, talks about how many times a data set element repeats. So let's assume I want to find the arithmetic mean of the data set containing 3 5s and let's do 2 7s, okay? So the mean of this data set is going to be equal to 5 plus 5 plus 5 plus 7 plus 7, all divided by 1, 2, 3, 4, 5, right? Now remember, we're going to be working with the frequencies, so notice that this can be rewritten as 5 times how many times the 5 repeats, and then 7 times how many times the 7 repeats. And the denominator is precisely the sum of those frequencies. So one can propose that the arithmetic mean can be calculated as the sum from k is equal to 1 to c, where c is the number of unique elements, so in this case the numbers would be 2. The unique elements times their corresponding frequencies, all divided by the sum of those frequencies, right? So that's going to be the closed form representation of that. And this formula actually has several applications and occurrences in several different fields, finance being one of them. So for example, if we go back to our original example with our larger data set, with 4, 5, 7, and 10, then the arithmetic mean of that particular data set is going to be equal to, so we had 4 2s, we had 2 4s, we had 6 5s, there should be a plus sign, so 5 times 6, and then we're going to have 3 7s, and then we're going to have 4 10s, all over the sum of the frequencies, so 2 plus 6 plus 3 plus 4, and once you work out that math, that's going to give you 109 divided by 15, and that's going to be approximately equal to 7.3. So you can calculate the arithmetic mean from a frequency distribution fairly easily. So what other things can you do with a frequency distribution aside from calculating the arithmetic mean? So another type of frequency distribution that is commonly used is what we refer to as a cumulative frequency distribution. A cumulative frequency distribution. Some people will call it a CFD. So let's start off with our particular frequency distribution that we have. So x and f of x. So we're going to have 4, 5, 7, and 10 with corresponding frequencies 2, 6, 3, and 4. So the cumulative frequency distribution I'm going to abbreviate by capital F of x. So what the cumulative frequency distribution of a function is it is equal to the frequency value of x plus the sum of all of the frequency values that precede it. So since x is the very first element of this particular data set, the cumulative frequency of 4 is just going to be equal to 2. It's just the frequency of that number. It's the least value. Now, stuff starts to get interesting when you proceed down the list. For example, what would be the cumulative frequency value associated to 5? So it's going to be the frequency value of 5 plus the sum of all of the frequencies that precede it, right? So it's going to be 6 plus 2, or 6 plus the cumulative frequency that preceded it. So that's going to come out to 8. So what would be the cumulative frequency of value associated to 7? So that's going to be the frequency of 7, which is 3, plus the frequencies of all values that preceded it, 6 and 2, for example. Or you can take 3 and add it to the cumulative frequency that preceded it, which is going to be 3 plus 8, which is going to be 11. And then finally, what would be the cumulative frequency value associated to 10? So that's going to be the frequency value associated to 10 plus all of the frequencies above it, or the cumulative frequency that preceded it. So that's going to be 4 plus 11, that's going to be 15. Now, very important, what is so significant about this particular number? So this is always going to be equal to n, which is going to be the sum of the frequency values, right? So that's one way you can always check to see if this cumulative frequency distribution is correct. Now, another important property, so can we graph the cumulative frequency distribution? Yeah, sure, there's nothing really stopping you about that, but the interpretation is going to be slightly different. So we have 4, 5, 7, and 10. So keep in mind that 10 is going to correspond to 15. That's always going to be the sample size. And each of the columns that precede it, for example, 11, 8, I guess doesn't really look like 8 compared to 11. So it probably would look more like that, and then 2 is something significantly smaller. So notice that if you were to either look at the bar graph representation or the scatter plot representation, it is always going to be an increasing function. And that's one of the properties of cumulative frequency distributions. So f of x, or more precisely capital F, is an always increasing function. Because it's cumulative, it should be additive as you move down the domain of your particular function. So that is the cumulative frequency distribution. Now, what's so useful about this? Like, what does this achieve for us? So one application of the cumulative frequency distribution is being able to quickly calculate the median from the cumulative frequency distribution, which, remember, the median is a measure of central tendency, and it is also a measure of position because it's the center quartile for a data set. So let's just briefly review how we calculated medians from the standard data set representation. So for an odd data set, so let's just choose 5 elements, so x1, x2, x3, x4, and x5, and let's just assume that this is a ranked order data set, so each of these elements are less than its next value. So we know that x3 is going to correspond to the median. So one important question is, well, how do we get the rank or the index associated to that particular element 3? So 3 can be found by taking the sample size n, which is 5 in this case, adding 1 and dividing by 2. So in general, the rank associated to the median is always going to be n plus 1 over 2. That's always for odd cardinality data sets. And for even sets, so let's choose 6, so x1, x2, x3, x4, x5, and x6. And let's again assume that this is a ordered data set. So remember that the median of an even is going to be the average of these two elements. So for example, how can we find the index of the smaller one? So the index of the smaller one, k, which is again equal to 3, is going to be equal to the sample size n divided by 2. And in general, k is going to be equal to n over 2. Where this is even. So xk for odds is precisely going to be the median, and for the even data set, the median the median for an even data set, is always going to be equal to xk and xk plus 1 added together divided by 2, right? So here xk is x3 and xk plus 1 is going to be x4. Take them two, average them together, and that gives you your median. So that's just a brief review of how we can calculate the median if it's listed from least to greatest in a set representation. But what if you have 5 million elements? Are you really going to order that entire data set and then, cancel out from the left and the right and figure out which one is in the direct middle? No, it's not practical. So what we can do is we can use cumulative frequency distributions to rather help us with that. So remember, the sum of our data set, or the sum of the frequencies for our example, came out to 15, which is odd. Right, so the median of this data set is going to be the direct middle element of this particular data set. So let's again look at our cumulative frequency distribution that we constructed. So we have 4, 5, 7, and 10, and 2, 8, 11, and 15. So how can we interpret the data set from the cumulative frequency representation? So the very first minimal element of this data set is 4, and we have 2 of them, right? So that means x1 through x2, all of these elements are going to be equal to 4. So we only have 2 4s, so the next element must be 5, which is going to start x3. And remember how many 5s we had? We had 6 of them. So x3 is going to be 5, x4 is going to be 5, x6 is going to be 5, x7 is going to be 5, all the way out to x8, which is also going to be equal to 5. And notice that I didn't really have to count them out, because notice this last element corresponds to the cumulative frequency associated to that particular element. By chance? No, not at all. And you can continue this pattern. So the next element will be x9. So x9 through x11, which is going to be elements 9, 10, and 11. So we have 3 7s. All of these elements are going to be equal to 7. And x12 through xn, which is x15, the 100th percentile, is going to be equal to 10. So what do we know? So since the cardinality of our data set is an odd number, the rank associated to the median is always going to be equal to m plus 1 over 2, which is going to be 15 plus 1 over 2, which is 8. So element 8 is going to be the last element of the second category. So since all elements are from 3 to 8 are equal to 5, this means that the median of our data set is equal to 5. And that's how you can figure out the median of a data set. So let's assume that our data set was even, and let's assume that the numbers are the same. So if that was the case, then we would have 8 and 9 as our elements. So 8 is going to be equal to 5, and 9 is going to be equal to 7. So the median would be 6 in that case if we happen to have 16 elements in this data set. But it's pretty straightforward. As long as you can figure out which elements are equal to what, it should be fairly straightforward. So that is the frequency and the cumulative frequency distributions. So what other things and what applications can we do with frequency distributions? So the next application of frequency distributions, or I guess you could think of as an extension of the frequency distribution, is going to be relative frequency distributions and cumulative relative frequency distributions. So let's start off with the same exact starting point as we did before. So we're going to have x and our frequency distribution of that particular value of x. So we're going to use the same example 4, 5, 7, and 10 for the frequencies 2, 6, 3, and 4. So the relative frequency distribution, which I'm going to abbreviate as f sub r of x, is going to be equal to the frequency divided by the total. So remember, the total, which is going to be the sum of the frequency values, was equal to 15 for our particular data set. So we're going to take the frequency and divide by 15. 6 divided by 15, 3 divided by 15, and 4 divided by 15. And you can do like an approximate decimal rounding of this. So that would be approximately 0.13, approximately 0.40, approximately 0.20, and approximately 0.27 as the relative frequency values associated to each of these elements. And before I go into some applications of that, let us just go ahead and talk about the cumulative relative frequency distribution, which is going to be capital F sub r of x. So we're going to calculate this the same way as the cumulative frequency distribution. So the cumulative relative frequency of a particular value of x is going to be equal to the relative frequency of x plus all of the relative frequencies that precede it. So by default, the very first value is always going to be 0.13, and then we're going to add it to 0.40, so that's going to be 0.50 or 53. So 0.53, and then 0.73, and then the last value will be 1.00. And this is always going to be 1. The cumulative relative frequency distribution value associated to the maximal element will always be equal to 1. Why? Because 100% of the data should be less than or equal to that particular value, right? And keep in mind that the sum of all of the relative frequency values, frx, is always going to be equal to 1. Similar to this statement, capital Fr of x maximum always will be equal to 1 as well. So these two statements are practically equivalent, just from two different perspectives. So what is the application associated to the relative frequency distribution? Well, they clearly give the percentage or the proportion of the data set that is associated to that particular value. So let's just write that down. So Fr of x gives or describes the proportion of S that is associated to that particular value, x. Okay, so that's what the relative frequency distribution value is. Now, in terms of other applications of FR and capital FR, they're going to be more targeted when we start talking about probability mass functions and probability density functions. But you will see these concepts in the near future, so don't think that they are completely useless. So now we have 4 different sets of distributions, right? So we have the frequency, the cumulative frequency, the relative frequency, and the cumulative relative frequency distributions for a particular data set, and all of them will offer some unique information. And we discussed, how to calculate the measures of central tendency, at least one of them, measures of position. So that's also useful. Also keep in mind for the relative frequency distribution, notice that 13% of the data is going to be less than or equal to 2, and 40% of the data is going to be less than or equal to, no. So if we look at the cumulative relative frequency, 13% of the data is less than or equal to 14, and then 53% of the data is less than or equal to 5, and then 73% of the data is less than or equal to 7, and 100% of the data is less than or equal to 10. So you can see a very obvious application of the cumulative relative frequency. These numbers can help us get percentiles, right? So that's an obvious application that we could get from the cumulative relative frequency. So now we have an application for frequency, relative frequency, cumulative relative frequency, and cumulative frequency. So now we have a very easy application of each of them. So that's pretty great. But what about measures of deviation? So can you calculate, for example, the sum of absolute differences and the average absolute deviation of all of these things, like the standard deviation, the coefficient of variation, stuff like that? And the answer is yes, of course. So let's look at how we could calculate the standard deviation from a frequency distribution, for example. So calculating the standard deviation from the frequency distribution. Okay, so you should be able to verify that the standard deviation formula can be rewritten in terms of frequency distributions as the sum from k is equal to 1 to the number of unique classes in the data set of xk minus the sample mean, and let's assume this is for a sample, right? So not a population, squared times the corresponding frequency of that unique value, all divided by the sample size n minus 1. So the sample size n minus 1. So it'd be the sample standard deviation. So recall for our example that the mean was equal to 109 over 15, or approximately equal to 7.3. So how would we find the standard deviation of our sample from our frequency distribution? So if that is the case, the standard deviation is going to be equal to the square root of 4 minus that mean value. Don't use the rounded value, of course, because you're going to have an accumulated round off error. So 4 minus x squared associated to the value of 2 for its frequency. And then the element of 5 has a frequency of 6. The element of 7 has a frequency of 3. And the element of 10 has a frequency of 4. And then we're going to divide all of that by the sample size 15 minus 1. And then once you work all that out, you should get approximately 2.3238. Of course, remember, you could just do this from the original raw data set, but this is extremely important if you have several millions of elements where repetition is evident. Now, can you also analyze, for example, skewness from the distribution of a data set by looking at its frequency distribution? And the answer would, of course, be yes. So let's look at how we would analyze a data set by looking at its frequency distributions. So I'm going to be writing a continuous representation of the data sets. For example, I'm just going to write some smooth curve, so like that. So this is just an extrapolation of a discrete set of frequency distributions associated to a bunch of data values. So just keep this thing in mind. It need not be a continuous data set in order to generate this graph, but sometimes extrapolation of those points helps you see more of a geometric pattern. So sometimes it can be useful to extrapolate the points. So when we see a graph like this, notice that we have some outliers chilling out in the upper spectrum or the tail of this distribution. So if the majority of the data is hanging out here, right? So majority of the data is here, but we have some tails that are chilling out on the right-hand side of the data set, then we call this data a skewed right distribution. So without graphing, is it possible to possibly determine whether the data appears to be slightly skewed right or skewed left, or maybe relatively symmetric in the center? The answer is yes. So remember, there's two measures of central tendency that we can calculate quickly from the frequency distribution. We can calculate the median and the arithmetic mean. So remember, the arithmetic mean is heavily more skewed by outliers. So if there's an outlier in the right-hand spectrum, the arithmetic mean is going to be closer to the outlier compared to the median value of the data set. So the skewed right distributions typically have the characteristic that the arithmetic mean is larger than the median. So if you have a data set and the arithmetic mean is larger than the median, and you were to construct a frequency distribution for that data set, then it is likely that that data set will be skewed to the left. Skewed to the right. Similarly, if you have another data set, so let's assume this is our data set and we have our tail over here, and the majority of our data set is hanging out on the right-hand side of the data set, and we have a couple outliers chilling out over here. So the outliers on the left, or in the left tail of the distribution, then we're going to be referring to this data set as skewed left distribution. So again, the arithmetic means are going to be more heavily impacted by the introduction of outliers. So the mean is going to be closer to the outliers compared to the median, well, because the median is a little bit more well representative of data when outliers are introduced. So skewed left distributions are really common when the arithmetic mean is less than the median. So these two things are usually true at the same exact time. And I emphasize the word usually because it's not always the case. So we have skewed left and skewed right distributions, and we have these two different properties. There's actually two other graphs that are actually really common that you should be aware of. So the very first one, maybe you've seen in several different books, whether they be statistics books or other things, and it usually has this bell curve type of representation. So you usually refer to this type of shape as a symmetric. So a symmetric data set. So in this particular picture, usually the mean and the median and also the mode, because that corresponds to the highest frequency, are usually approximately equal to one another in a symmetric data set. So if the mean is approximately equal to the median and also equal to the mode, or approximately, then this is a symmetric data set. But there's another scenario that is not often discussed, and it's a distribution like this. So you have data sets that are sort of following this parabolic, this arch type of shape, right? So again, where's the mean and the median going to be? So the mean and the median are going to be hanging out in the center, just like the other symmetric case, because this is also a symmetric data set, but the mode is not in the middle. We actually have two modes. We have mode 1 over here on the left, and we also have mode 2 on the right-hand side. So this will be a bimodal or a multimodal data set. Okay, so those are two of the most common symmetric relationships that can come out in the data sets. But also keep in mind, as we just mentioned before, if we want to determine the skewness, pretty much where the tail of the distribution is located, then you can easily just analyze the median and the mean and then see which one is larger than the other. So to close this discussion of frequency distributions, we're going to briefly talk about class-based frequency distributions, which are commonly used if repetition in the sample set or data set is little or non-existent. Take, for example, this data set I have listed here, and I'm just going to call it S, just because. So notice we do have some repetition, in particular of 7 and 9, which have a frequency of 2. So technically one could say that this is a bimodal data set, but the frequencies of 7 and 9 are practically equal to the frequencies of the rest of them, which are all practically equal to 1. So if I were to just construct a repetition-based frequency distribution, I would practically have a flat or approximately uniform. So every time you see a flat distribution, usually it's called a uniform distribution, but we have a couple little, bumps there. So this is approximately uniform. And of course, approximately is a subjective word, but it's practically a box, right? So when you have an approximately uniform frequency distribution that's based on repetition, a class-based frequency distribution might be a good alternative representation for your data set. So in order to construct a class-based frequency distribution, the very first thing you need to do is construct or define your classes. So your classes are going to be a partition of your data set. So for example, one way we can partition the data set is to choose a number that's less than the minimum, for example 0, and then we can choose a number that is higher than the maximum, 14, which we can say is 15. And we can then break down this data set into a bunch of smaller classes. For example, I can choose the interval 0 to 5 as my very first data set, and then I can do 5 to 10 as my second data set, and finally I can choose 10 to 15 as my other data set. And clearly, if I call this set A, this set B, and this set C, then clearly A union B union C in terms of the elements are a partition of this data set S, because every element is in exactly one of these, and every one is pretty much accounted for, right? So that's a partition. So once we create our classes, or our categories, whichever word you prefer, so then you can calculate the frequencies of values associated to each of those classes. So how many elements are in 0, 5, not including 5? So that's going to be 0, 1, and 4. So the frequency will be 3. What is the frequency associated to class B? So that's going to be equal to 5, 7, 7, 8, 9, and 9. So the frequency of that is going to be 6. And the frequency of class C is going to be equal to 1, 2, 3. So keep in mind, ABC must partition this data set S. You cannot count a data value more than once, and every one must be accounted for. There are some exceptions, rare exceptions that can be used for this, but for example, exclusion of outliers is a common one. But this is usually the pattern that we go by. So now that we have our little frequency distribution that is based on classes. So we have our classes, which are A, B, and C. Our frequencies are 3, 6, and 3. Then we can construct a representation. So A, B, C, so this is X, and this is the frequency of X. So X here corresponds to a class of values, not necessarily a particular value. And then we have 3, and then we have 6, and then we have 3. And then you can color this whatever pretty colors you prefer to color it, right? So this is our frequency distribution, our class-based frequency distribution for this particular data set. And you're like, okay, well, it appears that my mean and my median are equal to each other. Now, when you do class-based representations, it's not really numerical, at least in its original sense, because now A, B, and C are categorical variables, because these are categories, not necessarily numbers. Some people will choose point estimates for each of these intervals. For example, you can choose the mid-range, for example, 2.5, 7.5, and 12.5 as sort of representatives for these classes, and then treat all of the elements in each of those classes as those point representations. So for example, all elements in class A gets a new value of 2.5. All elements in B get a new value of 7.5, and all values in class C will get a representation or a new value of 12.5, and then you can calculate your mean and the median based on those things. But you can probably see that very different sets will have very similar metrics if you approach it in that way. So I'm not going to talk about that in more detail, but you should be able to see some of the pros and also the cons associated with that. But let's at least outline the basic structure of how to construct class-based frequency distributions, just in case you did not get that down. So the very first step is to determine the lower bound. So the lower bound, let's call that lower bound L. For example, in our particular example, we chose L to be equal to 0. And also we need to choose our upper bound, and we can call the upper bound U. So for our example, we chose an upper bound equal to 15. And then you need to say, okay, how many classes do you want to break up your data set in? So now this is a very, very sensitive question, because how many classes you decide to partition your data set can give you very different graphs. For example, I chose 3 for this particular frequency distribution. If I were to choose more, it's possible that I get a distribution that is more approximately uniform. And you should be able to see that each of these two distributions represent completely different messages. So it's easy to mislead your audience if you choose the wrong, or possibly that's your intent, so the right number of classes to represent your data. So for our particular example, we chose 3, and we get this very symmetric data set. And then once you decide your classes, then you need to define your class width. Class width typically should all be the same for each class. There are special circumstances where you may want your class width to be a little bit different. For example, ages. You may want to group your 0 to 18 people together, your 18 to 30 people together, your 30 to 40 people together, your 40 to 60 people, and your 60 and older people together. There are some certain cases where class width not being uniform is preferred, but that's only on a case-to-case basis. But if you're looking for a uniform class width approach, then that would just be the upper bound minus the lower bound divided by the number of classes that you have. So for our particular example, that was 15 minus 0 all over 3, and that gave us a class width of 5. So that gives you a couple different approaches for how to represent data, either in a repetition-based or a class-based representation of frequency distributions. And we also talked about a few applications of frequency, relative frequency, cumulative frequency, and cumulative relative frequency distributions, and some of the things that they can be used for. So in the next video, we're going to talk briefly about two-dimensional data, when you have an x value and a y value associated to a particular measurement or set of measurements, and sort of how we can analyze data in 2 dimensions or maybe even higher. So I hope to see you there, and I hope you have a wonderful day. Take care.